So we have a lot of data, and we didn't just like compile it and put it in notebooks. We actually tried to compile it, analyze it, and interpret the results in lieu of some management guidance. So that's what I'm going to talk about. So there's a couple of topics we want to go over first. The water quality in the Keys. People have been sampling water quality in the Keys before we did. And so we're going to summarize what they found, compared against what we found, that sort of stuff. And why are we even talking about water quality? This is about weed management. Well, because weed management actually has the potential for benefits and the potential for unanticipated adverse impacts. So that's what we're going to talk about in a little bit greater detail. Positive changes and negative changes that can occur to water quality associated with weed management. And then that kind of gets us to the final point, which is like, are there ways to quantify this information so you can provide some kind of management guidance? And that requires a loading model. We need to know where the nutrient, what's the nutrient of concern? Where is it found? And where did it come from? Are all important things for us to kind of deal with. And that's what we're going to go through. So if anything I talk about, you're not quite sure, just raise your hand, because everything feeds on itself, right? So we're going to talk about water quality, then we're going to talk about where it is, and then we're going to talk about a model. So if there's something you want a little bit of clarification, hey, please raise your hand, because that'll help you understand where we get to in the end, which is the most useful part of it, I think, is the so what. So the water quality in the Tahoe Keys. So Tahoe Keys and its consultants have been monitoring water quality for years now. And we're going to first off look at the water quality data they have, find out whether or not we actually find something very different, or we find kind of like the same thing. Is there a trend analysis? Can't do trend analysis with 1 year. So we're going to go back and look at the totality years. So you can see that they've been sampling both in the Marina Lagoon, the main lagoon, and a couple stations in the lake itself, and then also in Tahoe to the south. So what did they find? This is the same data on the left and the right. It's just that on the left-hand side, this is total nitrogen. I'm going to call it nitrogen from here on out, but if you really want to pay attention to it, total nitrogen includes inorganic, organic, particulate, dissolved, everything together. And it does matter. And what I've done on the right-hand side is I've truncated the y-axis, because this number right here is high enough that it makes it hard to see the differences in these ones. So I just changed it from 5 down to 0.4. So nitrogen and phosphorus, we're going to talk about. If you want your lawn to look green, you add nitrogen and phosphorus oftentimes. If you want your water to look green, you add nitrogen and phosphorus. But nobody wants their water to green, so we want to keep nitrogen and phosphorus out of our water, which means we have to find out where it came from in the first place. So the nitrogen content in the water, you can see that 2012 was a really high number. This is basically all the stations in Tahoe Keys combined, and the average is over 4. That's a higher number than you'd see from stormwater runoff. So that might mean a couple of things, like a sewage spill, I don't know, fertilizer runoff that actually was a really high value, or it could be cyanobacteria. Cyanobacteria are harmful algal blooms, right? And they can make nitrogen out of the atmosphere. And if you're a scuba diver, you know 78% of the air you suck into your lungs is nitrogen gas. It's a form of nitrogen that, like most plants, can't access, but cyanobacteria can. So it's a possibility that you might have had a cyanobacteria bloom here in 2012. On the right-hand side, that red line represents the water quality objective for the open waters of the lake, and that's 0.15 milligrams per liter. You can see that actually a couple of years you're pretty close to. This is the water quality objective for the lake, and there's a couple of years where you're pretty close to it, and we actually found the same kind of thing. The water quality in some of our stations was pretty close to that objective for the lake itself. So like 2008, 2011, we don't really see an overall trend in that data. Now let's look at phosphorus. Same thing, phosphorus, the concentrations are going to be lower because the nitrogen, the phosphorus content for living organisms is that there's a lot more nitrogen than there is phosphorus. That red line on the bottom there is 0.008 milligrams per liter. Now, a milligram per liter is a part per million. And so 0.008 means 8 parts per billion. That's a very low number. That's lower than the phosphorus criteria we have for Everglades protection, which is 10 parts per billion. But it's not that low of a number. We have in Biscayne Bay, which is off of Miami, and the Florida Keys, we have criteria that are actually lower than this. But it is a low number. 8 parts per billion is what we're talking about here. And you can see that you never were really below that in any of these years. And then also, I'm going to use this number a little bit later. So imagine a value of 0.28. We've fallen right about there. That's 28 parts per billion. I'll get to that in a minute, why I want to pay attention to 28 parts per billion. So in the year 2016, the prior report collected a lot of data, and it expressed it in terms of minimum values, maximum values, the mean and the median. Means and medians are averages, but they're calculated differently. And the difference between the two helps you understand what drives the data. And the point here is, again, I had to truncate the y-axis to show off the range of these lower values. Even the minimum values in 2016, from the Marina Lagoon, the main lagoon, and Talat, even the minimum values were higher than that. So remember, you had some years, 2008, where you actually were below it, but not in 2016, 8 years later. For phosphorus, the same kind of thing. Even the minimum values, even out into Lake Tahoe in 2016, were higher than the 8 parts per billion criteria here. But your means and medians are kind of in this range, you know. And so let's imagine that we have a mean value of 28 parts per billion would be kind of similar to what Lake Tahoe was, but higher than what we found in the Tahoe Keys in that region. So overall, there's no obvious trend we didn't see, but something odd might have happened in 2012 because it's a real outlier for nitrogen. It's not a real outlier for phosphorus, but it's an outlier for nitrogen. The Tahoe Keys regularly exceed the water quality objectives for the open waters of the lake. I don't think that's a surprise to most people. Now, what did we find in our sampling? Because we did more data for some variables that weren't collected before, and we did no stations in the lake. So this is basically, you're not supposed to read this, it's simply supposed to show you that on a lot of times we collected a lot of data. And so we've got all the dates we collected and all the water quality data. And I'm going to show you what I think are the highlights to help us understand how the system of the Tahoe Keys functions. So let's talk about what we found for nitrogen or phosphorus. I've got these shown as surface water and the bottom sample. So we sampled on the surface, and then we sampled right below the bottom. These dotted lines represent the water quality objective for the open waters of the lake. These are color-coded. So this is the Marina Lagoon, this is Talat, this is the main lagoon. And you can see that in general, there are a couple of locations where we were close to the water quality objective in the Marina Lagoon. So I want people to just kind of think, it's not like the water quality is really horrific in these places. And a lot of times, a lot of locations, we had water quality that met the objectives, just like we did in 2008. A couple of stations in the main lagoon, W4, W6, W10, tended to have better water quality than some of the other locations. W4, W6, and W10 were located closest to the connection to the lake itself. And some of the other stations were located more in like dead-end canals, if you would. So farther away, probably longer residence time, more stagnant conditions. So water can brew, if you would, for a little bit longer and get you a little bit worse water quality. And then notice as well that whether it's the surface or whether it's the bottom, Talat has a higher nitrogen content than the other two systems. Okay, so a little bit higher. And then for the most part, the last thing, the nutrient concentrations are a little bit higher in the bottom than they are in the top, which suggests the nutrients can be coming from the sediments to some degree, because the closer you get to source, the higher the concentration should be. So particularly in Talat, we see that. So a similar kind of pattern for phosphorus. Concentration is a little bit higher in the bottom than in the surface, particularly so for Talat. We have some values that are pretty close to the water quality objective in the surface water, and in general, Talat is higher than the other two systems. So if you think algae is all about nutrients, you'd expect Talat to have more algae than the other two, right? And we're going to express nutrients, we're going to express algae in units of chlorophyll A. Chlorophyll A is a pigment that every photosynthetic organism needs, whether or not you're a cyanobacteria or you're a sequoia tree, you need chlorophyll A. So it's an abundance indicator for phytoplankton. And what we see is Talat doesn't have the highest chlorophyll concentrations. The main lagoon does. And the Marina Lagoon has the lowest. Marina Lagoon had the lowest nutrients. Tallac had the highest nutrients, but Tallac doesn't have the highest chlorophyll. So that it's not as simple as just nutrients. There's something about Tallac, which we're going to talk about later, which makes it less sensitive to nutrients than the other two. And that's actually a good thing. You want to work with that. You want to maintain that. You want to take advantage of that good news. So we see Tallac is lower than here, which actually this place had lower nutrients than Tallac, but it's got more chlorophyll. And again, the lowest chlorophyll concentrations are 4, 6, and 10, the areas that are closest to flushing, which suggests that residence time has a lot to do with water quality as well. It's not just, nutrient concentration, it's how long the water sits around seems to be an effect on what the water quality is like. So we talked about these vertical profiles, and the reason why the vertical profiles are important is because it can kind of tell you where the action is taking place. And that can help you understand what's most important, the algae in the water column or the weeds that are growing attached to the bottom. So all of these plots have water depth and then oxygen. And as you go left to right, the oxygen is higher. And you can see the kind of bulge that goes out here, and there, and there, and there. It's not at the surface, it's a little bit deeper down. And what that suggests is most of the oxygen production, or most of the primary production, is not occurring at the surface. It's occurring a little bit deeper, which is where the weed beds are. So where the vegetation is, that's where most of the primary production is happening, which tends to get us to the point where we're saying the weeds are perhaps more important than the algae that's in the water column. And the other thing is, very low levels of oxygen are tough for organisms to live in, but they're not good for nutrients as well. If I've got phosphorus in bottom sediments and I have oxygen, that phosphorus is going to stay bound to the bottom sediments. If I have phosphorus in the sediments and I don't have oxygen, it's going to be released up to the surface. So when we try to figure out how important the sediments are, we have to take into account two things. What's the phosphorus content and what's the oxygen content? And if we know both of them, we can figure out how important the sediments are as a source of the nutrients that can give rise to an algal bloom that nobody would want to have. And we actually see that in Tallac, for example, the bottom, say, 8-10 feet has got no oxygen, particularly in station T13, which is farthest to the west. So farthest to the west, the bottom water has no oxygen there. So if we also had high phosphorus and we've got no oxygen, that would suggest that the sediments right here could be a nutrient source. But if the sediments are low in nutrients, then it's not going to be that important. But there are places where we don't have an awful lot of oxygen on the bottom, so we have to pay attention to what the sediments are like.